Hi, I'm Gansun Tech. I will explain about how to use Quartus for digital circuit and system design. We first need to know what our minimized logic expression is. We can derive it from the truth table and use K-map to get our simplified canonical SOP expression. As an example, based on our truth table, we have gained our minimized expression for the output to create the logic circuit, such as X is equal to AC, output Y is equal to BC, and output Z is equal to ABC. In order to create a logical circuit in Quartus, first of all, we go to File and click New Project Wizard. For the first page, we click Next. Then, at the second page, we need to save this project in a file that is easy for us to find and create a name for it. After that, in the next page, we choose Empty Project. Then, press the Next button one more times. We'll see Family Device and Board Setting. At Family part, we change it into ARIA 2GX. Then press the Next button until finish. After that, we click File again and then New. Then we go to Block Diagram or Schematic File and save as Block 1 or any name we want. Now, let's insert our input pin as A, B, and C. To add our logical gate, we can click the gate icon on the top here. For easy search of the specific logical gate that we need, we can type the name of the logical gate we need in the search bar. For example, we want a 2 input AND gate, so we type in gate N2 and click OK. Then connect the input with the gate and insert our output. Here is an example of our logical circuit. One we have made using basic logic gate, and another is using none configuration.
Hi, I'm Li Chen, and now I'm going to talk about my part is how to run the timing simulation and how to see the waveform of our schematic. Before we stimulate our logical circuit, first click Start Compilation. So once everything is compiled, we can start to stimulate our circuit. To stimulate, we click File and click University Program VWF, that stands for Vector Waveform. After we get it, we can see there is a timing diagram that runs from 0 to 1000 nanoseconds. We can change that by clicking Edit and Set End Time. Here we have to set it to 40 nanoseconds. Next, we press Insert our inputs and outputs in here. Click on Edit, Insert node or bus. Just click on Node Finder and click on List. We will get all our inputs and outputs of our whole circuit. Select all and click Move and OK. Next, we need to set out our input values, that is A, B, and C, that will be represented in the timing diagram. We have to make them switch on and off from 0 to 1 in different time periods. Click on C and click the clock icon that is called Override Clock. Set our period, for example 10 nanoseconds, and click OK. We can do the same for the other inputs. Remember, B will have double the period of C and A will have the double period of B. As an option, we can select our inputs and group them together to visualize better by showing what the binary numbers are. After that, we go to the stimulation and settings. It's important to remove the node V opt under the functional stimulation setting to enable us to run the stimulation. After removing it, just run the simulation by clicking the Run Functional Stimulation and save the waveform file.
Hello, I'm Kamalia Sofia, and I'll be explaining about the waveforms that's been generated by the functional simulation and timing simulation. This is the waveform we have generated by the functional simulation for our basic logic circuit. Based on this waveform, we have set our input signal interval to 5 nanoseconds. Therefore, every 5 nanoseconds, that signal will change the state to either logic 0 or logic 1. The output signal will change accordingly based on the input signal. For example, between 10 nanoseconds to 15 nanoseconds, the input signal is 011 for ABC. Thus, from here we can see our input signal is 010 for XYZ. Now, we can compare the waveform functional simulation to a timing simulation. A functional simulation is our ideal case without delays. We can see in our timing simulation for our outputs XYZ, there is this crossing. It means the output could not be processed by our logic circuit, therefore causing the output to be delayed. The output can only be processed after an average of 7.43 nanoseconds. For example, in output Y, the output was delayed to 7.33 nanoseconds. Lastly, let's compare our waveforms of the timing simulation for our basic logic circuit and the logic circuit with the NAND configurations. As we know, for the basic logic circuit, the output was processed after an average of 7.3 nanoseconds delay, while for the NAND configuration circuit, it is 7.52 nanoseconds. Despite this minor difference, we can still get the same output for both circuits.